Okay, our new topic is momentum, and basically momentum is a measure of how difficult it is to stop an object, I guess. You've got to apply a certain amount of force for a certain amount of time. But by definition, an object with more mass has more momentum, and an object with more velocity also has more momentum. So that's the formula there. So momentum is given by the symbol P, and it's measured in kilograms meters per second, because the mass on the other side is in kilograms, and the speed is in meters per second. So it's always going to be those units there, and it's just mass times velocity. So just bear that in mind there, mass times velocity. So if you're asked to put some things in order about what the size of the momentum would be, if you had a rocket on the launch pad, or a moving fly, a blowfly, so you had a blowfly moving around, that was moving, blowfly flying around. We could have a grain of sand, I suppose, blowing around in the wind. Or you could also use a high-speed car or a slow-moving train. So those are your objects there. So if you're being asked to rank order these from the lowest momentum to the highest momentum, you've got to consider both the mass and velocity equally. So it's just as important to have a large mass as it is to have a large velocity. So looking at this here, which one of those has a decent sized mass and a decent sized velocity, or which one has a very small amount of that? Now if you look at the rocket on the pad there, they've got a velocity of 0. So by definition, anything times by 0 here would be 0. So that should be the lowest one, number 1. Blowfly flying would have a lot more mass compared to a grain of sand. A lot more mass compared to a grain of sand. Even if they're both, one was blowing in a high wind and one was a blowfly moving at a relatively slow speed, you will find the one with the smaller momentum here would be that one with very tiny mass. It might only be 1,000th of a gram. Blowfly could be 2,000 or 3,000 times bigger than that, and the speed is not going to catch that up. So if you look at it like that, it gives you the second one. And obviously the blowfly flying is going to be number 3 rather than the car or the train. Now if you look at the car or the train, let's actually do an estimate here. With the car here, you might have a mass of say 1,200 kilograms there, or even if you guess 2,000 kilograms for a ridiculously large car. Times by a high speed, what would be a high speed? 40, 50 meters a second. That's really going over 150 k's an hour sort of thing. That's very fast, sorry. Going over 180 kilometers an hour. That's going to give you a certain momentum there. So for the slow speed train, it might only be going at say 1 meter per second there. So a typical value for a train, even a small one, you probably talk about 500 tonne there. So if you write in the 500 tonne, be certainly several hundred tonne. You've got that sort of number there, which is about 500,000, and that's easily going to give you more momentum than a high speed car, even if this one's 60 times by that. So in ballpark you're going to get that the blowfly is 3, the high speed car would be 4, and the slow moving train would be the largest one there. Okay, so it's important to realise that both the mass and the velocity have an equal sort of part to play. Something with a very large mass and a very large velocity will have a very big momentum. And they both got equal strengths there. Some people also mix up inertia with momentum, because something with a lot of momentum, which is moving quite fast with a large mass, will also have a large inertia. But a momentum can also occur with 0. Say the rocket on the launch pad there has a very large mass and has 0 momentum because it's not moving, but it has a lot of inertia still. So objects that are moving, consider that momentum and inertia could be very similar to each other. But the exception to that is that something that's stationary has a lot of inertia but no momentum, so they are slightly different, so be careful of that as well. The main thing to realise is that momentum has one key use, and that is that the total momentum before a collision is the same as the total after, and you can use that to solve problems involving collision. Typical questions would be where objects are collided together, and sometimes they stick together and sometimes they separate. Now the law you're going to use here is called LOCOM, or law of conservation of momentum, because it turns out that the total momentum beforehand as a total should be the same as the total momentum after. And that's a really useful law to go and work out what's happening in collisions to find the unknown things. So if you look at this one here, we've got 2 objects before. So you've got a momentum there of number 1, you've got a momentum of number 2, and afterwards you've got 1 object here. So 1 momentum afterwards. And I'm putting a dash there to indicate afterwards. So momentum 1 would be mv going to the right. I'll give a little subscript of 1s there. and momentum 2 would be m2 v2. In this case, is going left, so it is a vector, so we do need to consider direction. And afterwards, we've got a sort of a total mass there we'd have to work out, and that total mass would be times by the speed, so we need to work out the total mass there. So if you look at these here, we've got one at the top here of 6 kilograms going 2 meters a second to the right, plus 2 times by 4 to the left. So what you've got here is 12 right plus 8 left. So don't make the mistake of thinking that's a total momentum beforehand of 20. It's a momentum beforehand of 4 as a total. So that's what it should be afterwards according to the law. The after momentum should be the same. So what have we got over here? We've got one object made up of 6 kilograms and 2 kilograms, which is mean 8. So you've got a mass of 8 with an unknown velocity. How do you solve for that there at the end then? Well, this is 8 times by v dash. So we're going to just divide by 8 here on the other side. So you're going to go 4 divided by 8. We can pull this v dashed over here. You'll get a half a metre per second in the direction that you were getting before, that way. Okay, so the direction is being worked out. So that's the sort of typical question you would get with only one object at the end when they're joined together. Now, if you look at the next question here, these time they've actually separated after the collision, so you have to approach it slightly differently. But you still start it the same way, so you can actually cheat here and do a paste in there, edit paste, because you're still using the same law. And we're still going to use the idea of locom, this idea that total momentum beforehand is equal to the total momentum afterwards. So if you start with that again and go through the same process, you've got two objects, so we can actually say this is momentum 1, P1, but I'm going to shortcut this and just say I've got M1, V1 there going to the right, plus the second object, which has got M2, V2 for momentum going to the left. And afterwards, we've got an unknown momentum there for that object, don't know if it's going left or right. And we've got a known one, we'll call this 1 still by the way and call it a dash on it. You've got a known one for M2, V2, going this way. So this time you've got to actually focus on, this is separated so you can't do it as one combined mass like in the last question. It's a bit more difficult. So if you look at that, you've got 5 times by 8 going to the right, which is going to give you 40 by the way in the next line. You've got 10 times by 5 in the next part going to the left. So you've got 50 going to the left. So altogether, the momentum here, 40 to the right, 50 to the left, is 10 to the left. That's your momentum beforehand. Now that's what it should be as a total afterwards, so it helps you work out the unknown. Now on the other side, we do know that the mass of 1 is still 5, but we do not know its speed or velocity. We know that the mass of this one is 10, and we know it's going to the right 5. So what you've got here is an unknown one, which you're trying to sort of work out by rearranging, and 50 to the right. So to rearrange this and actually get v on its own, I would remove this 50 to the right first and put it onto the other side. So if you're going to do that, you would do this as 50 to the left now. Because it's switching sides, it should switch direction because it's now being subtracted. And you've got 5v dashed. So altogether we've got 10 left and 50 left. You've got 60 to the left here. Equals 5v dashed. To solve for v dash, we're going to divide by 5. So 60 over 5 will give you 12 meters a second. And this time it's going left because that's the way the momentum is going. Okay, so that's how you do those if they separate. Now the other type of question you get here is if they've started to be stuck together in the first place and then they exploded for some reason and separated, you can still use the same law. You can be nice and lazy there. I'm just going to shrink that down a bit. Okay, and again now we've got one object to start with. It's at rest though, so you could be really lazy here and go the total momentum beforehand is 0. None of the parts are moving, so you just treat it as a 0. Afterwards you've got two moving parts, an M1 and a V1 with a dash to show it's afterwards. And that's going left, and we know it's going left. And we've got an unknown one here, we don't know which way that's going to go just yet. So here you've got 0 equals 8 times by 5 to the left. And that's being added to a mass that we know is 2 kilograms and V2 dashed. So we know we've got 0 momentum to start with, so these two here added up together should give you a 0 momentum afterwards. So to solve for that, we're going to do this one here. 8 times by 5 would be 40 on this side, but on the other side it'll be 40 in the other direction because you're reversing it, because you're doing a negative vector on the other side. Because you're going to have got to add that vector to the left, we're going to add it to the right on the opposite side if you rearrange it. 2v2 dashed, that means v2 dashed should be 40 divided by 2. to do that opposite operation there, and that gives you 20 metres a second going to the right. So if you look at this, you've got 20 metres a second and 2 kilograms going this way, which gives you 40 altogether. And here you've got 8 fives of 40 going that way. So these two momenta here are going to be added together and give you 0, which is what we're trying to get anyway. So you can just check that answer and it does work. So they're the 3 key types of questions you get in just a one line and one dimension. Okay, thank you.